Hi, dear madams and sirs. First, I would like to thank all the members of the organizing committee of this conference who allowed me to present this oral communication, which is entitled Markov Decision Processes with Discounted Costs, New Tests of Non-Optimal Actions. For this reason, Markov processes are widely used to model decision problems. The communication plan is as follows. Firstly, we give some essential preliminaries which will be useful for this work. Secondly, we present results and discussion in this contribution. Finally, we end by providing the conclusion and references which have been used. Markov decision problem is formulated by this tuple. A set of finite states, a set of actions, the transition probabilities, the causes function, the discount factor. The general model of a Markov decision problem is given as follows. The utility function to minimize in order to find an optimal policy for solving our problem is formulated in the following definition. Since the state and action spaces are finite, the minimum of utility function is guaranteed. Therefore, the corresponding policy is also found. Since the same action spaces are finite, the minimum of the utility function is guaranteed. Therefore, the corresponding policy is also found. It is well known that the dynamic programming tool provides an optimal policy for our model. The following standard algorithm is the value iteration algorithm based on the Bellman optimality equation. To present our test for identifying non-optimal actions, we need to introduce the following lemma. This theorem gives a new test of non-optimality based on the previous lemma. Several results are given in the literature of action elimination procedures for improving the classic algorithm. Combining of the proposed test and the standard value iteration provide an iterative algorithm as follows. To show the scientific interest of our contribution, we have to give an illustrative numerical example. In this case, the numerical data in our example is given as follows. This graph represents or summarizes the previous numerical data. Hence, By application of algorithm 2, we obtain the optimal value vector and an optimal policy. Besides, the same algorithm provides approximate value of the test function as follows. In this numerical result table, the red color indicates the actions which must eliminate according to the state reached and the number of iteration. The algorithm which is already established makes possible to reduce the size of the action space. Hence, this allows reducing of computational complexity by being interested in minimum of iteration number when the elimination begins. We obtain the following numerical table. The results, or by transforming the previous table into a graph representation, we get in this context the indicator of actions eliminated at each iteration increases when the discount factor gamma increases. We notice the same graphic behavior by applying Summary and German algorithm in 2019. But in terms of spatial complexity, there is a significant difference. Finally, we conclude this work by, firstly, we illustrate the significant difference between the cited algorithms of action elimination algorithms. Secondly, we give a brief idea for the next work, thus we will be required to model the motion of a robotic drill. Next, we present the main references that are used to construct this work. Despite of many references which contributed in this work, we are limited to cite the essential of them. Thank you very much for your attention.